Right. So we have Mike here. He's talking a little bit about D&D. We're going to see how we're going to create our characters today, right? Go through a campaign, learn a little bit about how to evade the monsters that are in those dungeons. Probably roll for a little stealth today. So we'll see how it goes. Thanks.
All right, Colonel Khan, how you doing today? Yes, thank you for being awake. This is your first Colonel Khan? This is awesome. This is outstanding. I've been to a few conferences. I'm not a seasoned pro, but I've been to a few, and let me tell you, I like what I see here. So, today we're going to talk about Roll for Stealth, Intro to AV and EDR Evasion. If you want a copy of the slides, they are available online right now, redsiege.com/stealth. You can download the PDF. If you want to get a hold of me, mike@redsiege.com, Hardwater Hacker on Twitter. Feel free to download the slides now or later if you want, and I'll put up that link later. A little bit about me. I have been in IT for a bit, and I've been in security for a while as well. I like to do a lot of things that aren't computers. If you do not have a hobby that doesn't involve a computer, I encourage you to get one. It is good for your sanity, and I do a lot of that. So, enough about me. I want to set some expectations, what this talk is and isn't. So we'll start with what it's not. It is not an advanced evasion topic. We're not going to be talking about unhooking and obfuscating C2 comms and evading those checks that are happening at runtime. This is mainly about getting your payload either onto disk or in memory. So some techniques that you can get your payload onto the system, and then what happens once you're executing it, for the most part, is another talk. But this is that intro space. Gotta crawl before we can run. I'm also going to talk a bit about entropy checks, and if you're not sure what that means, I will explain it later on. So I want to start with things that get you caught. The things that we're talking about here are things that I have learned as a result of assessments, so things that have tripped me up. Things like just copy pasta a script off to GitHub and running it is probably not going to work if it's been around for any period of time. So some of those common examples would be like, if you're familiar with the MS build technique, anyone know what the MS build technique is? A couple of people. It's a way of executing code with MS build using a specifically formatted XML file. A lot of people use what's known as the 3G student template as kind of their starting point. Or a couple other well-known ones. But if you take those templates and don't change those templates, very likely there are things about those templates that are signatured that will get you caught before even your shellcode is part of the equation. Those are things like not changing variable names, not changing function names, not changing task names. So like in here, you can see it's using the task name class example. That's from the 3G student template. It's probably a bad task name to use for your test. Like, just come up with some name that's not that. There are a few other things here, right? Like funcadder. We're copying our shellcode called shellcode. These in themselves may not be something that will get you caught. hthread, thread ID, and pinfo. However, those variables existing in an XML file that is being accessed by MS build, like if you have an EDR or AV that's looking at things in context, that could be bad. So know that that's, things that could get you caught. Even things like comments. Now this is, we're hopping in the Wayback Machine a little bit, but this blog article that's listed, the first one, Pentest Armory, the author's talking about getting caught using PowerView, and the thing that tripped him up was actually these 3 lines of comments. That's what the AV detected on. Symantec detected those comments, removed those comments from the PowerShell script. It was just fine. It wasn't looking at anything else. It looked at the comments, and that's still a valid approach today. So if I run PowerView, I have a stripped version of PowerView that I have removed all comments from there. So I'd encourage you to do that, because even the comments in things like interpreted code, so PowerShell and VBA scripts and things like that you're running on a Windows system, those could get you caught. Black Hills talks a little bit more in this blog about modifying the Mimikatz PS1 to run on, I forget which AV they're running against, but it's that same concept. It's old, but it's still valuable information. Know that those comments could trip you up. This one is talking about not obfuscating common code execution patterns. It might be, the virtual alloc and the RTL move memory, and then create thread, whether it's that kind of pattern, or the example that I have on screen here is C# code. You'd probably find this in an MS build template that you want to execute shellcode with. So to be able to allocate memory and to execute code, I need to import these functions from kernel 32. So that's what you're seeing here. We're importing from kernel32.dll. We're going to import virtual alloc so we can allocate memory that we're going to copy in our shellcode. And then we want to execute the shellcode created, so we DLL import from kernel 32, create thread. This pattern right here is enough for a defender to tag your XML file as malicious with MS Build. You don't have to have any more code. Just the presence of these two DLL imports in an XML file being accessed by MS Build, Defender says, I know what's up. This isn't legit, and it's going to trigger on it. So we're going to look at a way that we can get around that in a little bit. Another thing that might get you caught in things like compiled code could be the strings that are in the compiled code. So this is a screenshot from Defender Check, I think I'm using. Defender Check, but there's also a slightly updated version called Threat Check. The way it works, if you're not familiar, it does a binary search. So it takes your payload, it splits it in half. So it has two equal sized chunks, submits both chunks to Defender. If one of those chunks has a detection, it takes that chunk, splits it in half, and submits both halves to Defender until it narrows down on exactly the bytes that are causing the detection. In this case, I was trying to get Mimikatz to work against Windows Defender. So the blog's linked down there at the bottom where I went through this, getting around signature-based AV. So Mimikatz worked. I just need to do things like change Mimikatz to Mimidogs. Rename, and yet that is the most common way of getting Mimikatz to work. It does work. But in this case, what you're seeing here, this is an error message. Module not found, error Mimikatz _ do local. So that is the error message that gets printed out if Mimikatz runs into certain errors. And that's what Defender Check was flagging on, was this message. So you may have to change your help messages. You may have to change debugging output that's put out by the program. These strings that are in here could be something that could get you caught. Another thing that could get you caught is entropy. And I will talk about it, but not yet. So we have to talk about evasion. We talked about a few simple things that get us caught, that get us tripped up. How do we evade those checks? We need to make our malicious payload look legitimate. Please tell me people see it here. Please tell me. All right, good. All right, like people just all of a sudden stop reacting. What's going on? 1 second, please. So I need to make my payload look legitimate. And there's a few ways that I can do that. First, I want to talk about a problem that I had. So this is an alert from Defender. Says it thinks that this file Zor optimized is whackattack.b, so it thinks it's malicious. So what this was is a shellcode loader that I have, runs a Zor routine or an XOR routine with a multi-byte key. Instead of just using a single byte, uses a multi-byte key. Shellcode loader has worked for years. All of a sudden, one day, Defender's flagging, saying, hey, this is malicious. So I'm trying to figure out what is the problem. And because I am an excellent programmer, I debugged this by putting in a bunch of printf statements, right? Like, what is the problem? But now my program doesn't run. It's still just like, I don't even have a chance to run it. It's on disk, and Defender's like, this is bad. Okay, well, next step, how do we figure out what this is? Well, if you don't know in your code base what's causing the detection, the easiest way to figure out is just start removing pieces of your code base. So I start removing pieces of my code base. And pretty soon, the only thing I have left is the XOR routine. It's like, oh, okay, this is weird. So I start trying to change it. And I declare a variable, and then I add a variable, or add something to that variable, and I declare another variable, and I multiply those together and add, subtract, divide, do a bunch of different things, and finish up my XOR routine. And it's still getting detected. Every variation. And if you remember the screen from Defender Check, it tells us exactly, okay, it's this size and at this offset is where the badness in the file is, at that offset. Every time I change and recompile, it's telling me the bad bytes are at the exact same offset. I know it's the XOR routine, and I know it's happening at the exact same spot. Gave it away, but who can guess what the problem is based on the name of this slide? Yes, sir. That's right. Compiler optimization. I was racking my head, like, what is the problem? My coworker Justin said, like, maybe it's compiler optimization. I was like, please, it's not compiler optimization. It was. And the reason that was, like, compiler optimization looks at your code and it tries to make your code leaner and faster and use less memory and be more efficient. So it saw all of the junk that it was trying to do to obfuscate XOR and was just like, we don't need any of that. So it's getting the same routine every time. And apparently using XOR with a multi-byte key in the wild is not something that legitimate software does. So all I did was disable compiler optimization, no threat found, didn't change anything else. So if you were compiling payloads, turn off compiler optimization. Talked about entry points being a problem. So you can rename your entry points. I encourage you to go read these links. They talk about if you write C# code, they will give you some information on entry points. So this is what a typical DLL import looks like. We're DLL importing from kernel 32, could be another DLL, but in this case, kernel 32. And then basically this is the declaration for virtual alloc. Like this is what virtual alloc looks like. When you call it, it takes a uint32 for the start address, uint32 with the size, allocation type, and memory protection settings, right? So this is how you need to set up using virtual alloc in C#. This is bad. This pattern is bad. But there are some options to virtual alloc. We can do things like set last error, exact spelling, but the key part is this point right here. I'm saying DLL import from kernel 32, but instead of just calling it good, I'm saying I'm using the entry point virtual alloc. Set last error, exact spelling is true. And then the rest of this is the same except for this part here. Now, there is no magic to the word Splendid Dragon. That is just what my random word pair generator came up with the day I created this slide. What's magic about this is that now when I want to allocate memory, I don't call virtual alloc. I call Splendid Dragon in my code. And I've changed up this brittle signature. I talked about brittle signatures earlier. This brittle signature for this by simply making it a little different. And if Defender or another EDR starts detecting this, I can swap exact spelling for set last error. They're not, the order doesn't matter. Whether they're true or false may not matter for your program. So you can change these around and change the signature. The cat and mouse game, they change, we change a little bit. And it's these stupid, dirty little tricks that work. And this trick still works today. So that's one way of making your code blend in. There's a lot of ways of doing it, but that's just an easy thought. And we're going to go into more. It deals with entropy. But now we need to talk about our shellcode, because even if our shellcode loader is good, we have shellcode. And shellcode has certain patterns of bytes. They're always going to be the same. If you're doing Cobalt Strike and you're using the latest version of Cobalt Strike 4.8, and you generate 100 different beacon.bin files, there are certain bytes that are going to occur in the same order in the same places every time, because shellcode has its own loader inside of it, right? Like it's a program just converted into bytes. So those programs have to have certain bytes in certain places because they're the loader for the program. That will get you detected. So we need to make our shellcode not look like shellcode. One interesting way of doing it is shellcode as UUIDs. Anyone know about this technique? Okay, we got 1, 2 people. So back in 2001, I believe it was, 2001, NCC Group releases some research about the Lazarus Group and what they were doing. And there were a couple of interesting things. One was how they were executing the shellcode. They were using enum system locale A to execute their shellcode. Really weird. Let's find out what the locale of the system is and then hand it a pointer to some executable memory. Makes no sense, really, but it works, and it still works today. But the other part that was really cool about it was how they were obfuscating their shellcode. They structured their shellcode as a UUID, a universally unique identifier. Maybe you've heard of a GUID as well, globally unique identifier. For our purposes, they're the same thing. And if you're using UUIDs and using the libraries correctly, you generate a UUID for each user of your application, and you can generate a UUID for every person on the planet, and you shouldn't have a collision. So these UUIDs have a specific structure, and they work, they're a certain pattern of bytes. Turns out, formatting your shellcode to make it look like a UUID, which is simply a matter of making them however many characters long and putting hyphens in the right place, is enough for EDRs to be like, seems legit. So Bobby Cook came up with this Ninja UUID runner. So it's a shellcode loader that uses enum system locale A and has a Python utility, bin to uuids.py, that will parse your shellcode into UUID format. So it ends up looking like this. Your shellcode, these are all your shellcode bytes. Probably pop calc for this, but it's just structured as a UUID. A certain number of bytes, dash, bytes, dash, bytes, dash, bytes. This is it. And this works today. I did this a couple of weeks ago and Defender was like, seems legit. I didn't encrypt my shellcode at all. I just pasted my shellcode in UUID format, and it still works. Stupid simple trick, but it's something that works. So I encourage you, if you are an offensive person and needing ways to get your payloads going, this is a good way. If you are a defensive person, I encourage you to know about ways that the attackers are getting around detection. So some other things that we can do. You could take your shellcode and just reverse the bytes. So you have however many bytes, just reverse the array. And that works against some EDRs. I don't know what this is. It's just backwards. And then you reverse it right before you use it. You could try breaking it into chunks, and that does work. I would encourage you not to do that, though. I said earlier that bytes occur in a specific order and in specific places. So you have to now know exactly where those orders are and where the boundaries are that you can break up. And if you don't, and if that changes, you've broken it up into chunks, and it's a hassle. It's worthwhile as an exercise to learn how to do it, but it is a pain. Another technique that my coworker Justin came up with, divide your shellcode into 2 arrays of even and odd bytes. Now, not even and odd by the value of the shellcode, even and odd by their position in the array. So if you have 100 bytes of shellcode, the first byte at position 0 is going to be an even byte. So we put that in the even array. The second byte at position 1 is going to go into the odd array. The third byte goes into the even array, however you want to do it. But split those up and then store that in your shellcode loader. And now when you want to use your shellcode, you just read the bytes basically backwards, alternating between those 2 arrays and copying them into a new array. And now it's very unlikely that the sequence of bytes that you've created, the 2 arrays, by setting them up like this, is going to lead to a detection. Steganography. How many know what steganography is? All right, awesome. Like, it depends. Like, sometimes you ask with steganography and it's like, no. So I don't need to explain it to you. Modifying the least significant bit, usually of the color data, lots of times of the alpha channel of an image, just changing for each pixel, changing the alpha value, the least significant bit, is a way of storing, encoding information into an image without significantly affecting the quality of the image. And a lot of ransomware actors will use this type of technique. And all it looks like is your loader is going and grabbing an image off of Twitter. If you follow Justin Elsey on Twitter, he had a proof of concept for this not too long ago. Like, grab an image off your Twitter profile. Probably not a great idea right now since the service is. But somewhere, throw your shellcode in an image, and it probably works. Another thing that works really, really good that shouldn't is using different languages. A lot of times we write our shellcode, our loaders and our malware in C or C++ or C#. And they work great. Those languages have been around forever. There's all kinds of proof of concepts out there for you. There's all kinds of libraries available for you. It's great, super powerful. But because they've been around a long time, there has been a lot of visibility instrumented for those languages. So if you are writing something in C or C++, or especially C#, like C#, you just use dnspy and basically like on the fly decompile your application and be like, aha, I see what you're doing. So there's a lot of visibility that's been instrumented for those languages. As a result, it makes it a lot harder to hide. The bad things, the nefarious things that you're doing are much more obvious. So what you can do is write code in an alternative language like Go or Nim or Rust. And Go has been around long enough now. Like, each of these languages kind of goes through this curve where it's new and no one's writing code in Go. So Go people experienced this early on. No one's writing code in Go. So if you're writing code in Go, I don't know what it is, but obviously you must be trying to hide something. So Go binaries that were like hello world, we're getting alerted on. And that applies even to other things. If you're familiar with the Veil framework. So if you're familiar with the Veil framework, it's a way of obfuscating your payloads. Chris Trunzer and a couple people worked on that. So they were finding that a simple hello world program, all it did was print hello world, was being tagged as malicious by an EDR because it was compiled with MingW on Windows or on Linux. Like, simply MingW compiler on Linux, this must be bad. Didn't look at all about what it was doing. Just said, I see what compiler and operating system, it's bad. So the same thing kind of happened with Go. Like, hey, this was written in Go. Same thing with Nim and Rust has happened sometimes. Recently, I was working with just writing a simple shellcode loader in Rust, and I didn't do any real evasion other than encrypting my shellcode. And I found that Defender was flagging without even the presence of shellcode in the binary, just compiling a program that imported the ARC4 or the AES crate and basically declared a new object to decrypt or encrypt AES or ARC4 or whatever. That was enough. Defender said, hey, this is written in Rust and I see you're using encryption. You're trying to hide something, you must be bad. Nothing else in the program. So these languages can work great, but you need to be aware of the target that you're at, because in some cases, the use of the languages signals that you're trying to hide something, just like using encryption and entropy. So we're going to talk about entropy now. So I want to make a disclaimer. I am not a mathematician, so I may not be explaining these concepts completely correctly, but I'm going to do my best job. We're going to talk about entropy as it relates to information theory, not the heat death of the universe. Although these things are related, we're going to stick with computer science. So we're going to talk about information theory. We're also going to talk about something called Kolmogorov complexity. So let's talk about entropy and find out why it's important. Roughly speaking, if something is high in entropy, it can be said that it is more random. So something that is higher in entropy, has more entropy than something else, is more random than something else. I said Kolmogorov complexity. Kolmogorov complexity says that if something is very random, it is not compressible. Something that is more random than something else is less compressible than the less random thing. And we can test that. Now, yes, I know you can use the Linux utility ent to measure entropy, but it's not installed by default on every operating system. gzip does this for you, just easy. So I'm going to read in 1,000,000 bytes from dev-urandom. So assuming I have a suitably well-written random number generator, I read in 1,000,000 bytes and I pipe it to gzip. This is just trimming out the rest of the noise. We don't need it. It tells me 0.0%. This is the compression ratio. So it was able to reduce the size of 1,000,000 bytes of data from dev-urandom by 0%, which means my highly random data that came from a good quality random number generator, it's very random, very high in entropy, is not compressible. So this leads us to a little bit of a problem. We typically encrypt our shellcode to try to hide it, unless we're doing something like the UUID trick. We encrypt our shellcode in one or more ways. And encrypted shellcode is, when we encrypt things, it makes them very random. So because it's very random, it increases the entropy. So there are different ways of analyzing the entropy. Like you could analyze entropy in the different sections of a PE. Like, is it in the R data or is it in the text? You know, some will look at that level. We're just going to take a more generic, higher level look at the entropy of the binary as a whole. So, little diversion, little side trip about entropy. So I mentioned earlier that you should rename like functions and variables in your scripts. And you might be tempted to be like, all right, I'm just gonna write my template and use random characters for those names. Do not do that, because certain AVs and EDRs will look at your variables and function names and analyze the entropy just in those particular things. And if your variable and function names are highly random, it's a sign you're probably trying to obfuscate something, which is a sign you might not be trustworthy. So using random strings for that may not be a good idea, which is why I came up with a random word generator for it. And I use word pairs instead of single words, because depending on the language you're developing in, certain words may be a reserved word in that language. So there's a chance that you have a collision, and now the word that you used is a reserved word in the language, breaks your loader. Using both character or two words together, very little chance that those are going to lead to a collision. So if you're writing scripts, do this. Wow. That's great going on. All right. So how do we lower entropy? Back to our compiled programs. One thing we know is that languages like English and German and, whatever, are not random. We know this. We can test this. Let's take an English dictionary and let's compress it with gzip. We reduced the size by 64.7%. So we compressed it by quite a bit. Probably not very random. Take a German and compress the German dictionary almost 76%. So it was even more compressible. So because of Kolmogorov complexity, we know that German is less random than English. It is lower in entropy than English because we can compress it more. So we know that languages aren't random. This is a very interesting article. They actually talk about like encoding your shellcode into text. So imagine taking like a Shakespeare sonnet and embedding that in your shellcode loader, and then like that is your shellcode because of the position of characters in the sonnet is your shellcode. Like, it's wicked. It works. I am not smart enough to explain it to you. So I would encourage you to go read about this because it's fascinating. But like everything, I'm here to talk about things that I learned on tests. And yes, I realize that CrowdStrike's right up here as a sponsor, right out there. And I'm sorry, CrowdStrike, I'm not picking on you. This is just what I learned. So I was testing against CrowdStrike's machine learning AV component, or a machine with that enabled. It was the CrowdStrike Falcon sensor. All right, let's see the time. CrowdStrike Falcon sensor with machine learning AV component enabled. I throw my executable with my AES encrypted shellcode on the box, and I try to run it, and nothing happens. I mean, a window didn't open up and then get closed. I didn't get an error. Falcon didn't register any alerts. I checked with the client. They're like, no, we didn't get anything. The program doesn't run. Copy it over to my machine, run it. Okay, it works. I know it works, but it won't run on their machine. So because I'm an excellent programmer, I recompiled my program with a bunch of printf statements. It says got here, got here. So the first thing that should have happened when I got into main is printed out, got here. Nothing happened. So that tells me my program didn't get killed. It never ran to begin with. And if it never ran to begin with, Falcon had to be using information about, essentially metadata, to make a decision whether or not my payload was trustworthy to run or not. Because it never actually tried to execute it and blocked it. It just wouldn't run it. So I'm trying to figure this out, like what could be the cause. Talked over with some people on the Bloodhound Slack. Turns out, we kind of all agree it's probably entropy. So I use a trick, basically declare an array full of English words and compile it. And because we know that compiler optimization ruins our fun, we disable compiler optimization. I now have an array of English words, a bunch of words in my shellcode loader, and it works. And I'm like mind blown. So what is happening here? So let's take a look at it. There we go. All right. So this is literally a screenshot from the shellcode loader that I wrote. Unsigned char, anti-entropy, 7,740 characters. There's no magic to that number. That is how many words were in the English dictionary that I was reading my words from. Yeah, just compiled this array in there. And Falcon was like, seems legit. We're going to let it run. Now, as I mentioned, this is just getting our payload onto disk. Like, I had to have techniques to evade detection once it's running. But this was just about getting my payload running. So, why did it work? So, you see here, AES and AES plus words. AES.exe, it's small. It's only 362K, like in the world of shellcode loaders. That's not terrible. It's not great, but it's not terrible. We can only compress it by 18.4%. We take our shellcode loader with all the words in it. It's 15 megs, not ideal because I disabled compiler optimization, so it made it really big, but in days of fast internet, who cares if your shellcode loader is big these days? It doesn't matter, really. I can compress it by 97.8%. So because of Kolmogorov complexity, this is very compressible, so we know that it's not very random. It's low in entropy. Versus this one is high in entropy. I don't have a measure of the entropy because I can measure that with int. It will actually tell me on a scale of like 0 to 8, 8 being perfectly random, 0 being completely not random. We don't know, but Kolmogorov complexity works as a proxy, so we can use gzip to say that this is not very compressible, therefore it must be high in entropy. Another side note, some researchers back in 2019 came out with this Silence, I Kill You. So this research was really fun. They found that they bought the home version of Silence's next-gen machine learning AV, buzzword bingo. But that engine was the same engine that's in their commercial product. So that's true for a lot of vendors. If you want to do some research on how XYZ is going to affect your next campaign, you can probably buy the home version of XYZ a lot cheaper. It's going to use the same engine. May not have all the same features, but the scanning engine's probably the same. So these guys did that. They analyzed it. Well, what they ended up finding was that there was a really popular game at the time. I don't remember the game. There was a really popular game at the time, and their AV was marking this game as bad. And so it kept blocking the game. And of course, people were getting really ticked off because this is the most popular game in the world. They wanted to be able to run. So Cylance's fix was to take all the strings from the game. And basically, if these strings exist, confidence score 100. This is a good executable. So these guys found that out. They took these words, they figured it out by analyzing the payload or analyzing the Cylance file. They took the words and basically added those words to the top 500 malware samples at the time. And every one of them was Cylance, just like, please come through, please come through, please come through. So not entropy related, but I thought it was interesting and it's worth knowing. And, you know, go buy a home version of whatever, and you might have the next bypass and great blog and new hotness. So the world is open to you. Encourage you to do research. So much better than hot, spicy V8. If you ever get iced and you don't drink, you get the hot, spicy V8 and shake it. I did not know that trick that you're supposed to shake it. So I drank the first part. I was like, this isn't so bad. It's kind of like, I don't know, kind of like tomato soup. And I got to the sludgy, spicy part at the bottom of the can. Great experience. Okay, so another little side diversion, not related to entropy, but because it is related to entropy because what I added to here. So another way of sometimes getting around AV or EDR is making your file so big that it's too expensive to scan. And so a lot of engines will be like, oh, this file is 100 megs or it's 150 or 250 megs. It's going to take too long to scan this, and that's going to have a business impact. So I'm just going to assume it's okay. Bless you. So there are tools to do this, to artificially inflate files. Optiv, it's not Scarecrow, Mangle. Optiv has a tool called Mangle that they wrote that does this. It pads with null bytes. Some other tools I found pad with random data. Now, both of those options can be bad. Some engines look at a file, try to determine, has it been padded? And if it's been padded with null bytes or random data, it's like, hey, you're trying to hide something. This is bad. If you pad it with random data, you've now increased your entropy, and something that's doing entropy checks could catch you. So I took a little bit different approach. I wrote a tool called DigDug. Arcade game fans know what I mean. DigDug says, how big do you want this file to be? Takes your file and it reads from a dictionary and then appends enough data to make it that size. But because we're using words, we don't have the entropy problem and we don't have the null byte problem that some are looking for. And just adding all these words on the end of an executable sounds like, how could this possibly work? And yet it does. So DigDug can help you lower your entropy and get to a point that the engine decides not to scan it. Not picking on CrowdStrike, it just happened. We were testing against it like 2 weeks ago. My coworker Corey did that, and CrowdStrike was just like, 250 meg loader? Looks legit. Allow it to run, and just allowed it to go. So here's another tool in your toolkit. You can get it on my GitHub. All right, a little bit more on Evasion. So I have a tool that I wrote called Jargon. Jargon, the actual definition for jargon is like, it's a noun. It is words or expressions that are used by a particular profession or group and are difficult for others to understand. So if you've ever worked for a TLA, you know all about acronyms, or if you're in the military, you're all about acronyms. That is jargon. TLA is jargon for three-letter agency. So it's words that people outside the group don't know. So this seemed like a good name for this tool. So let me tell you about the tool. We know that languages help us lower the entropy. If we put non-random data in a file, we lower the entropy. We know that languages aren't random. And we know that trying to decrease our entropy is good. So how can we use this to our advantage? What if we could have a shellcode loader that contained no shellcode? It doesn't load shellcode from somewhere else. It just contains no shellcode, but it is a shellcode loader. What would that look like? I was thinking about this problem after I was working on the previous CrowdStrike bypass that I showed you. Now, I want to say that I am not the only person that has come up with this idea. I believe it was talked about in The Art of Hacking, one of the volumes, I believe, or maybe another one of those books. I don't know. Someone told me about it. Other people have written tools that do what I'm going to show you. I just couldn't find anyone who had published it at the time that I had. So I am not like super smart and invented this. I'm just like the first person who published it. Everyone else was like, I'm going to keep this tool to myself. Whatever. Okay, how does it work? This is even more needlessly complex than it needs to be, but stay with me for the ride because I didn't realize this until I was explaining it recently. So we normally write our shellcode as like hex characters. If we want to put in a 0, we put in 0x00. We want to put in, 255 because we start numbering at 0, put in 255 for our 256 character, we put in 0xff. And that's what our shellcode looks like. It's structured different ways. Sometimes you have to escape the X's with a backslash, but we're writing our shellcode in hex. Mind blown moment for me was realizing depending on how you declare your character array where you're storing your shellcode, you can actually store your shellcode as an int. I was like, wait, how can I use this to my advantage? But here's where it gets needlessly complex. Like I did this conversion to int or thought about it as an int, but you can actually write arrays and loop over an array like 400 and never even have to worry about this integer piece, right? Like, so some people were like, wait, why did you do that? I don't know, man. Like, I'm not that good of a programmer. Like, this is just how I bashed my way through it. So how does it work? Imagine a world where you have 256 unique words. It's important that the 256 words, you have to have 256 of them, and they have to be unique. And the reason is because each one of those words is going to represent an individual shellcode character, essentially. So I need something to represent 0x00. You use the word attending. I need something to represent 0x01. You can use promptly. 0x02, Terry, so on and so forth. So now I have 256 unique words in a translation table. Now I used an English dictionary here, but the words could be anything. The words could be strings from kernel32.dll. That will really mess with an analyst's mind. Like, what is going on here? Take all the strings out of the executables that occur in the Windows directory and then grab random ones. As long as they're unique, and if you're doing this in C, it has to be a valid string literal. So like there's certain characters that aren't going to work. But as long as it's a valid string literal for the language that you're doing this in, there's 256 unique words, you have now created a translation table. We talked about this. So now we just need a Python script or something that looks at our shellcode, looks at the byte value in each position in all of our shellcode, and then looks at the lookup table and says, oh, that's a 0, I'm going to put attending in. Oh, that's a 1, I'm going to put promptly in. And when it's done, you have this shellcode array of words. Contains 265,730 words because that is a Cobalt Strike Beacon, and that's how large it is. This many bytes in this array. It's gigantic. It's painful. Depending on the language you do, you have to declare this different ways because your compiler will just give up and die. Many times I'm trying to figure this out. But this will work. Now, in our shellcode, when we want to use this, we've got our translation table and we have our translated shellcode. We have that in our loader. So we've got these arrays of words. Now we just need to loop through our array, starting at 0, going through the last byte of shellcode, because that's how large this is, 265,730. Then for each position, for each byte in that array of these words, for each position, if the first word is Dutch, I loop through all the positions in my translation table and find the value of the position. If it's in the first position, it must be 0, right? The first because we start numbering at 0. So whatever the first position is in the array, we hit it, we went, oh, that's first position. I'm going to insert 0 into my payload array. And then we're going to break out of the loop because we're going to go to the next position of shellcode. If you're using certain languages, you don't even need to do a for loop. Like you can just do a lookup of the index and get the index of that word. But as we loop through every word in this array, we find out what the value is for this and insert it. And again, I'm inserting it as an int essentially, but it could be hex. Like it's the same thing. It's not, but it's the same thing, and it works. Think about it later. Like, it makes my brain hurt. But this works. Does it work? It does. It is smaller than the other way I showed you. The other way, it's a 15 meg shellcode loader. This is 1.7 megs. Pretty small, not great. What about, compression and entropy? Remember again, our AES encrypted shellcode loader. Same shellcode. It's the same Cobalt Strike beacon, just using AES encryption. 18.4% compression. So very random, not very compressible. My version, with the shellcodeless shellcode, 85.8% compression ratio. So it's very not random. It's very low in entropy. So this gets around the entropy problem. We don't have to use any encryption routines, so we don't tip our hand by importing encryption libraries, depending on the language that we're doing this in. And we don't have shellcode bytes that are recognizable. So this is one way of using your shellcode. But does it work? Let's see. We'll click on it. Hey, we're translating your shellcode and receive beacon. So this does work. This is a valid technique. We've used this on tests. It has not been discovered yet. I don't know as an analyst really how you discover this, other than, hey, maybe it's weird that this executable contains so many words. That's weird. You could do, if you're a type of encryption analyst, you could do character frequency analysis and be like, hey, this word occurs so many. You know that in a typical shellcode loader, like certain bytes are going to occur so many times in so many positions, and then use character frequency analysis to be like, hey, this is maybe bad. Other than that, I don't know how you detect it. But it doesn't really matter because this is just allowing you to get the payload onto disk or into memory. I still then have to use OPSEC safe techniques for allocating memory, copying this into memory, and executing that code, and then I have to operate safely afterwards. So this isn't like easy button game over. This is just one piece of the equation. But this, if you're looking for that piece of the equation, this is a handy tool for you. You can get it on my GitHub. It's on there today, and you can laugh at my terrible code, but it's a little Python script. It's really inefficient, so it takes a long time, but it will generate a C stub for you. It doesn't give you a full shellcode loader, because I'm sure you can write a better one than I can, but it will give you your translation table, you translated shellcode, and that little for loop to decode in your program, and it'll work. So, all right, we're getting close on time. A couple other things to talk about really quick. As I said, I am not the first person to come up with this concept, and there are funner concepts. Someone's got one using Pokemon names. They use Pokemon. Same thing, 256 unique Pokemon characters. Those are non-random, and now you've lowered your entropy, and you don't have shellcode. I also found out after I had done that, last year at DEF CON, sometime after I had written that tool, someone released this talk at DEF CON where they used emoji for shellcode. And it achieves several of the same goals, right? We lower our entropy because of the kind of data that's in there. We obfuscate the nature of our data, and we do it in a way that doesn't show that we're trying to obfuscate what we're doing. So this is a really fun one, using it as emoji. I'm not sure this works for Intel architecture though. I think it's natively only for RISC-V, or RISC-V, but you could port this technique to Intel. Just want to get up on my little soapbox. Cobalt Strike is not dead. You just need to put in a little bit of work into the Arsenal kit and into your shellcode loaders, and there's a lot of life left in it. Most of the people getting caught running Cobalt Strike just aren't using the Arsenal kit to their full potential. So if you have it, please use the Arsenal kit. There's a lot of techniques that are still out there, and it's a very valid tool. A couple of resources. If you're not familiar with Sector 7 and their training offerings, I highly advise you to take these courses. I think they're $250, maybe $300 for the course. And I learned so much going through those courses. And those give you the techniques that you need to use for the second talk, how to get your shellcode running without getting caught. So there are these courses, I think about $250 a piece. Really great resources. I am not associated with Sector 7. I just people ask me well, where can I go to learn this? And these are great resources for fairly cheap. So I encourage you to take a look at it. Again, if you want these slides, you can get them at redsiege.com/stealth. My tools are on my GitHub. I am Hardwater Hacker, and Jargon and DigDug are the tools. Mike at Red Siege, if you have any questions. I'm Hardwater Hacker on Twitter. I'm on LinkedIn. Red Siege, I'm the principal consultant for Red Siege Information Security. If I didn't mention that, we do offensive security stuff. We have stickers in the CTF room and on the tables in the Lockpicking Village. If you like stickers, there's probably some left. Follow at Red Siege on Twitter. You'll find out about the Wednesday offensive, that we have cool people doing interesting things in the offensive space every Wednesday, 12:30 to 1 Central. No slides, no BS, just come and hear about cool stuff. Feel free to join in the conversation and hop on our Discord, redsiege.com/Discord. Ask questions. We would love to have you there. I would love to answer your questions now, and if you don't want to ask them now, feel free to hit me up on Twitter, LinkedIn, whatever. I'd be happy to answer them later. So with that, thank you, Colonel Khan. Any questions? Yes, sir. Sure. So the question was, have I tried it with different languages, not programming languages, but actually like Mandarin or French or whatever? I haven't, but it should. The idea should work. I wouldn't think that one would be more prone to detection than the other, but I haven't tested it. So, any more questions? Otherwise, I'll be around. Yeah, there's a question over here. Someone, yes. What kind of policies do we have for CrowdStrike? That's the problem. Is I don't get to see what the customer has most of the time. Like they just tell me like we got alerts, we don't. I don't know. Fairly locked down is what I can tell you, but I don't know to what extent. And that is a good point. What policies were configured with CrowdStrike or with different AV and EDR? They vary depending on the EDR. And the technique that works on one system might not work on the other. Like the first time I tested Sentinel-1, I thought, what is the big deal? This thing is a joke. I could do anything I wanted. Then I went to my next test and got punched thoroughly in the face because I didn't make any attempts to hide what I was doing, and they were using a different policy, and it was like Fort Knox. So the policies could make a big difference, something to be aware of. More questions? Okay, I don't think so. This is me in the cyber shirt. I'll be around for the rest of the day. Unfortunately, can't be here tomorrow, but thank all of you.